All right, guys, we're going to talk about imaginary numbers today. So, kind of the story goes, somebody's just like, what if I square root a negative number? I know we're not allowed to do that, but what if? And so that's kind of where this whole thing about imaginary numbers sort of started. So you guys have two things. We have our book here, and then we kind of have this bigger book. On the inside of this, there's a really fun pattern to look at, but that's not really going to be the focus of my video for you guys. So I'm going to use this to write on the front, where you guys are going to take some notes. And then on this page, I am going to write some stuff around this book, so I'm just going to use the back of this to kind of do that. So I'm actually going to start here. So what an imaginary number is again, when some dude was just like, okay, if I square root a negative number, specifically -1, because I can always split up a negative number into like, so let's say we're square rooting -25. I can just split that up into 25 times -1. So we can always just reduce it down to a -1. And we're going to call that the imaginary number I. It's literally like he's assigning this value to this variable. Kind of like if I were to say, no matter when we see x, x is always 2, which would be really inconvenient because x isn't always 2. But in this case, because we're using this special letter I, which I always put a tail at the end, so like we don't think it's a like a 1 or something, the letter I is going to stand for the square root of -1. Kind of a better connection is like the letter pi stands for the number 3.14159 forever, okay? So that's kind of why we do that. Now a little note that I want to make about this is an imaginary number. So we never replace I with the square root of -1. We only go the other way. So like if I see the square root of -1, then I replace it with I. So basically if you see this, you'll call it that. However, I can square both sides, and the moment I square both sides, I get that I squared equals -1. And now I'm back in real land. And since I squared is a real number, whenever I have I squared, I will replace it with -1 because that's real. So like if you see this, you're always going to replace that with -1. If I can take something that is unreal and make it real, then I should do that. I shouldn't go the other way. I shouldn't take something that is not real and make it not real. So if that kind of makes sense. Now, once we get into imaginary numbers, like we have like a real need for them in what we're doing currently with quadratics, because sometimes we square root things and sometimes those things are negative. But there's this whole other thing that we can talk about when it comes to imaginary numbers, and just like how can I interact with other imaginary numbers and other non-imaginary numbers. So once you kind of bring imaginary numbers into the equation, if you have real stuff and imaginary stuff, you have what's called a complex number. So for example, something like a plus bi would be complex because a is real and bi is imaginary. Okay, so once we and we always want to put the real part first, imaginary part second. And then kind of we're going to see this in a second here when we start solving. Like again, the purpose for imaginary numbers for us is because when we're solving, we square root negative things. But when equations with imaginary solutions are solved, they always come in conjugate pairs. And what a conjugate pair is, kind of like an opposite. But you've seen lots of conjugate pairs because we always have a plus or minus the square root of a thing. I answers or imaginary answers come in conjugate pairs as well because we're square rooting. So a plus or minus bi is a conjugate pair. You have a plus bi and a minus bi. So a conjugate pair is just where I swap the signs in between. So don't overthink it too much. They're important for reasons that will become apparent later. Okay. So again, here is what we're using imaginary numbers for us. When I'm solving a quadratic, I might have to square root something, and that something might be negative. So both of these are in vertex form. So I should be able to solve just by getting x alone. So like I would subtract the 4. Then we'd have x minus 3 squared equals negative 12. And then we would square root. And previously it was so nice. We would say, not possible, we are done. But now, since we've talked about square rooting negative numbers, we are going to continue further. And so the way that I want to break up this 12 is I really want to call it negative 1 times 4 times 3. And the reason I want to call it that is because I can square root negative 1, it's I. I can square root 4, it's 2. And 3 is just kind of what's left. Okay, so when I square root all of this, I should have smushed this down a little bit more. The square root of 4 is 2. We want the real part first. The square root of negative 1 is I. We want the imaginary part next. And then if there's any square rooty stuff left, we want that at the end. Always plus or minus when we square root. So that's kind of where we get this conjugate pair. Again, we kind of always want real imaginary root. The reason we want the root at the end is because we don't want to be confused about what is under there. If it's at the end, then I know that that's the last number under there and nothing else is under there. And then last step in getting x alone, we're going to add the 3 over. Now this is an imaginary number over here and it's got a root on it, so I definitely can't add the 3 with it. So we're just going to have this real messy answer, 3 plus or minus 2i root 3. So again, conjugate pairs, 3 plus 2i root 3 and 3 minus 2i root 3. Okay, let's try another. Again, we're in vertex form right here. I can tell because there's only one x, and so I'm just going to get it alone. So we'll subtract the 9. Then we want to square root. And here's where previously I'd be like, oh, no solution, but now we know how to square root a negative. And really I know how to square root 9. That's just 3. So because the negative is there, it's really going to just be 3i. Whenever I square root, always plus or minus. Then over here to get x alone, we're going to subtract the 6. Now 3i is imaginary, so I can't really combine that with a non-imaginary number. So we'll have negative 6 plus or minus 3i. And then we'll have to divide by 2. And we're dividing everybody by 2. So when you do, you could kind of leave it like this because 2 doesn't go into everything. Or you could split it up and like divide the 2 here for negative 3. And then just leave this 3 over 2i at the end. And again, fun little conjugate pair because of the plus or minus in between. Okay, so this is basically what we want I for. But there are so many other fun things we can do with I, so that's what we want to talk about next. Oh, well, let's jump one more. There we go. And we have all these different operations here. So if I have i's, I want to know how they interact with other non-I numbers. And basically it's like an x. You almost just want to treat it like it's its own variable. But again, I always want to leave imaginary stuff, but I always want to replace real stuff. So here, if I look in between, I notice that we're just adding. So I can add the real parts for 8. And I can add the imaginary parts. Actually, that's 0. So I kind of end up all real. So that's kind of nice. For part B, we are subtracting. And so for me personally, like I kind of like to distribute the negative so that I don't forget I'm subtracting everything there. And then I just go through and combine like terms. So like 4 minus 4 is 0. And then negative 3i is negative 6i. So only imaginary on that one. Here we are multiplying because the parentheses are smushed right up against each other. So like I'm going to do FOIL. So like first times first. Outer, we got 12i. And here's where it could get a little confusing. So like you have to be real careful when you add and subtract, and you can only do like terms. But when you multiply or divide, you can multiply, divide whatever you want. So like I can multiply real and imaginary numbers together. In the middle here, we get negative 12i And then last, we get negative 9i squared. So I squared is real. It's negative 1. So kind of what happens right here is this negative 9i squared. The I squared gets replaced with negative 1 because that's what it's equal to. And so really what I end up having here is 16 plus 12i minus 12i plus 9. So kind of the way I like to think about it is like the I squared just goes away and I change the sign right here. Like that's all that's going to happen. Okay. And so then I can actually combine the 16 and 9 because now they're both real. And so we'll have 25. And then 12i minus 12i, well, that's 0. So you just end up with 25, which is real cute. And this one here is actually also multiply. If I have 4 minus 3i squared, I'm going to write that twice and then like distribute twice like I did before. So we'll have 16, negative 12i, negative 12i, plus 9i squared. So the I squared is going to go away and change the sign. So really I'll have 16 minus 9 for 7. Oh my goodness. And then minus 24i. Heck yeah. Okay. So let's go back one more and talk about these ones. So quadratics with real solutions have 1 or 2 x-intercepts. Quadratics with imaginary solutions have no x-intercepts. So these are all real interesting because they have us thinking about it graphically, which I love. So like this is in vertex form because there's only one x. Has a vertex at 0, negative 3. So like there-ish. And then I notice that my parabola is pointing down. So I can tell that this has 0 real answers. So it will have 2 imaginary ones. Because it's not going to touch the x-axis at all. This guy here is also in vertex form with the vertex at positive 10, 5. So positive 10, 5, like there-ish. And then it's pointing down. Oh, so we'll have 2 real x-intercepts or 2 real answers. This one is also in vertex form because there's only one x with a vertex at 0, 25. So like here-ish. And then we're pointing down. So again, I think we're going to have 2 real. This one is in factored form, so like 2 real, because these are your x-intercepts, like negative 3 and then positive 12. You're pointing up, so boop, boop, like you definitely have 2 real. Factored form is so nice. Like if you're in factored form, you already know you have 2 real, because you should be able to see them. Like those are it. Back to vertex form here, we have a vertex at negative 4, 20, and then we're pointing up. So you're going to have 2 imaginary on that one. And then lastly, we have a vertex form here because only one x at 3, 0, pointing up. So because my vertex is right on, we have 1 real. And kind of no imaginary. Like if you have 1 answer, it's just because it's sort of repeated, which is real interesting. And we're going to talk about next chapter too. So now again, I almost feel like we covered it all. There's this real fun pattern about eyes in here, but really on the front, I was just going to talk more about how we mess with imaginary numbers. So just real quick, I guess a few more examples. So with imaginary numbers, we never replace I with like root negative 1. We always replace I squared with negative 1. Okay, so that's the big thing to remember. Like if I see an I, we're going to always leave it. We shouldn't replace it with like the square root of negative 1, but I should always replace I squared with negative 1. Okay, so kind of the big things when messing with imaginary numbers is just adding and subtracting. We basically treat them like x's. So again, if you have like 2 plus 3i plus 5 minus 4i. I know I'm adding because there's a plus sign in between. And so we're just going to combine our like terms. So we'll have 7 minus 1i. And you can put the 1 there or not. If you're subtracting, you just might want to be a little bit careful. Oop, geez. So if we have the same thing, but now a subtraction sign in between, maybe you want to think about distributing and recalling this like negative 5 plus 4i. So that when I look at this better, it makes a little bit more sense in my brain. Like 2 minus 5 is going to be negative 3. And then 3i plus 4 will be 7i. So I like to distribute the negative because sometimes when I get to here, I forget that the sign should change. So I just change it so I don't forget. The other thing that we can do with imaginary numbers is multiply them. So adding and subtracting, we have to be careful. We can only combine like terms, but with multiplying, we don't have to be careful. We can smush them right up and just multiply them up. The only thing we have to keep in mind is this is where I might run into an I squared, and I have to replace. So if we do first times first, we'll have 10. Outer, we'll have negative 8i. Inner, we'll have 15i. And last, we'll have negative 12i squared. So we replace that, change the sign. And then I do have 2 real parts, so we can simplify this to 22. And then I have some imaginary parts that I can combine, so plus 7i. And again, we always want real first, imaginary second. And then the last thing that we're not going to do a ton of, but let's talk about is obviously division or dividing i's. And so the thing about dividing i's is kind of like if you have a situation like 2 plus 3i over 5 minus 4i. You can't really divide anything there. However, there's kind of this weird rule where you shouldn't leave i's in the denominator. And that's kind of because you really have the rule where you can't have roots in the denominator. And this is technically a root. So the way you get it out is you multiply by a 1, because you can only multiply by 1, but it's a fancy one. And so you always want to multiply by the conjugate of the denominator. Now remember, conjugate is just kind of opposite, like we change the sign in between. And the reason that that works is because when it multiplies up, like if you kind of remember back here, these were conjugates. Those are same numbers, different signs in between. When you multiply something like that up, all of the imaginary stuff disappears and you're just left with the real stuff. So that will get rid of my roots in the bottom. So like if we think about multiplying the denominator first, because like we also have to multiply the numerator and we kind of have to FOIL both, so it's kind of a lot. But we'll do first times first, that's 25. Then we'll have 20i, then negative 20i, then negative 16i squared. Change the sign because we replaced. And then on the top, we'll have 10, and then 8i, and then 15i, and then 12i squared, which we will replace and change the sign. And so then along the top, we can combine like terms. So we'll have 10 minus 12 for negative 2, and then 23i. Now on the bottom, the i's cancel out to 0, and so we'll just have 25 plus 16 for 41. And like, because these don't all have something in common, I'm not really going to divide. I'm just going to leave it like that. But if they all had something in common, then I might divide it out and reduce it. But kind of weird, not going to do a ton of it. And I think that's where I'm going to leave it. So yeah, we'll see you on the next one.